Hello, everyone. My name is Elisa Waterman, and I'm the Chief Science Officer of FreeThink Technologies. And I'd like to welcome you today to the second in our FreeThink Technologies webinar series, selecting primary packaging for the stability for solid dosage forms. Our speaker this morning will be Dr. Ken Waterman. Ken Waterman received his Bachelor of Science degree from UCLA and his PhD in Physical Organic Chemistry from UC Berkeley. He then moved to the East Coast to conduct postdoctoral studies at Columbia University in New York. Ken worked for 12 years at Polaroid as a distinguished scientist developing imaging products, followed by 13 years at Pfizer as a research fellow working on drug stability, drug delivery, biopharmaceutics, and prodrugs. Ken is the author of over 75 publications and patents and was made an AAPS Fellow in 2011. Also in 2011, Ken founded FreeThink Technologies, where he is currently president. Before turning the webinar over to Ken, I'd just like to remind everyone that at the end of his talk, we'll be having a Q&A session. You can enter questions during the webinar by clicking on the Q&A link at the bottom of the screen. Thanks, and I'd like to turn this over to Ken.
Thank you, Elisa. So welcome everybody to our second in this webinar series. As you can see, we have recordings of the first webinar, which was on GMP ASAP, and you can find those recordings registering through the FreeThink website. This webinar today will also be recorded, and you can get copies of that afterwards. And there will be a webinar on June 23rd, which will be a joint webinar with IPA Canada. This will be an introduction to ASAP, so this should be especially good for people who aren't used to the ASAP system, and that's available also on the FreeThink website. So what I'm going to cover today is first just a brief what is FreeThink technology. Since we're sponsored, I give you a little bit of an overview of FreeThink, a little broad information about ASAP and ASAP Prime, not really going into a lot of detail. Then we're going to focus on how packaging, we're focusing here on primary packaging for solid dosage forms, mostly solid oral. Maybe another talk we'll give will be on other types of protection from packaging. But today we're going to focus on protection from moisture and protection from oxygen, and how do we select packaging for those two things. So first, about FreeThink Technologies. FreeThink is a company, we're now in our 10th year. Our main laboratories are in Connecticut. For those who are from other countries, that's halfway between Boston and New York. And we do contract research and development, problem solving, technology development. And we have our commercial software, ASAP Prime. We are an analytical company specialized in stability. We develop methods, do ASAP and traditional studies, everything from investigational through full GMP. We have a formulation development group. We tend to develop complex formulations for customers, and we develop new technologies of our own. The ASAP system is a process for determining drug product and drug substance shelf life in a short time. And I shouldn't say just drugs, we do things other than drugs as well, but typically less than a month. The samples are exposed for solids open to temperature and relative humidity conditions. And this is just a typical setup where you have a sample, here's a capsule in a vial. We use a saturated salt to control the humidity. The samples then are exposed to conditions designed to actually hit the failure point. So this failure point, the time to fail, is called isoconversion, and it allows us to use accelerated processes that don't work if kinetics aren't simple, but now work with this isoconversion process. And then we are able to determine packaging based on the calculated environment, which is something we'll be talking about today. And then there's aspects with respect to statistics. Typically, we work in probabilities, and most companies would like to have at least a 95% confidence for their shelf life. This ASAP technology has been applied to many, many types of products. So solids, including your common tablets, capsules, powders, but also lyophiles, soft gels, and patches. Liquids apply as well, although they won't be the subject of today's talks, but we've done many gels, solutions, suspensions, and ointments. Small molecules are clearly what the predominant work has been, but we've also done quite a bit on peptides, oligonucleotides. Biologics are beginning to get more emphasis, but requires that they be stored above freezing in the long-term conditions, and that the analytical methods have good precision. The kinds of things that we're able to use as the stability indicating changes include degradation products, related substances, assay, dissolution, crystal growth, change of appearance, and extractables and leachables. This is just a typical ASAP design where we have a number of ovens. These are kind of ovens we use, reach-in ovens. So the ovens only control the temperature. We use the saturated salts to control the humidity. And here are some time points. The number of repeats are in parentheses. So you'll notice that the time points are not evenly spaced. So for example, 2 days, 5 days, and 14 days. And that has to do with the algorithm with respect to the model fitting. Okay, so let's get started into how packaging can get developed without having to just put everything up in many packages and wait to see what happens. So to do this, let's understand first how humidity impacts drug product stability. So there are two broad modes where humidity affects the stability of products. And I'm going to call one of them sudden and one of them continuous. So in the sudden mode is typically by a phase transition. And we're going to talk about these a little bit more. The most common phase transitions that result in sudden failures in stability are related to deliquescence, which we'll talk about in a minute, and hydrate formation. The more common situation is that humidity works in a more continuous fashion. So the sudden defect means you hit a critical humidity, and as soon as you go above that, you effectively fail your product. Continuous is more longer at lower humidity will give you the same effect as shorter time at higher humidity. So it's a continuous function. Humidity typically the most common case is that humidity impacts the mobility of molecules, and by impacting the mobility, it increases the reactivity. So it's important to note that humidity sensitivity for solids is not typically connected to the fact that a reaction involves water in the reaction itself. So a hydrolytic mechanism does not have particularly high moisture sensitivity, and a non-hydrolytic mechanism does not have low moisture sensitivity. So it really has more to do with mobility. The second thing is that humidity can affect, again, in a continuous fashion, dissolution. So the reactivity with respect to loss of assay or formation of related substances, and also dissolution. And we'll see as well things like crystal growth from amorphous drugs. So let's talk a little bit about deliquescence. Deliquescence is a property of materials where it's related to how a material impacts the order or entropy of water itself. So it doesn't depend that much on the nature of the product, depends on how much disruption it has in the water. Another way to put it is it's very related to the solubility and how many species dissolve. So this property is such that when you're above the critical relative humidity, or CRH, a sample will pick up water in from the air and make a solution, whereas you're right below it and it doesn't pick up any water. So, I mean, a classic example is sodium chloride. Sodium chloride at 74% relative humidity picks up virtually no water. As soon as you go to 75% relative humidity, it will start going ahead and picking up water and making a solution. It'll keep making a solution. It'll keep adding water until it dilutes enough that the water activity now matches the external environment. This critical relative humidity is a sharp transition, and it depends on temperature because solubility typically depends on temperature. It only applies to very water soluble components. So I just wanted to pick a few examples of materials. Most common excipients do not deliquesce, and I would say that's not a coincidence. If you were going to figure out how to have a good general excipient, you don't want something that deliquesces. But there are some that are used for excipients. I picked a couple examples that are used in certain dosage forms, especially for chewable tablets and the like. So sorbitol deliquesces at 25 degrees. Its deliquescence point is 77% RH. So this would not be of concern if you're storing long-term at 25, 60% humidity. 25 degrees, 60% humidity, there's no deliquescence at 60% humidity. However, if, for example, you were storing it at 40 degrees and your package protection was not adequate, you could get deliquescence once the relative humidity exceeded 66%. As soon as it went to 66%, you would now deliquesce, you form liquid water. Once you form liquid water, you have a very sudden transition and you'll get changes. Similarly with fructose, um, again, these are sugars and sweetened. I tried to find a drug that had this property, and I did find one. This is sodium valproate, and it deliquesces fairly readily as well. There are drugs, especially older drugs, that have this problem. Rare that new drugs, you usually have to have at least, let's say, 200 milligrams per mil solubility to even have to worry about it. Another sudden change is the change between a hydrate and anhydrate, or anhydride and hydrate, depending on which direction you are. So this again is a sharp transition, and it does depend on temperature. So as you go up in temperature, the product, the drug, will tend to want to stay in its anhydrate form to a higher humidity. Or put it another way, to keep it a hydrate, you need a higher relative humidity. Sometimes this matters, sometimes it doesn't, but if you do have this transition, you may see a change in dissolution. It can go either way. So if you start out at an anhydrate, forming the hydrate may lead to poor dissolution. It could be if you're in a hydrate form and you dry too much, the anhydrate may lose the water of crystallization and form a amorphous drug, which would be chemically less stable. So just to find an example, this is an example from the literature of theophylline, and here's where that transition occurs. And you can see the transition varies with temperature, but it's in a region that we might be concerned about. If we started out in the anhydrate form, it depends on exactly what our temperature and humidity conditions storage, whether we need to protect it. Some drugs, this transition can occur at a significantly lower point and be more concerning. So if we suspect a phase change related to relative humidity, we need to identify the boundary in the temperature range that we're concerned about, typically 25 to 40 degrees. But keep in mind, if there is an excursion during shipping and there was a sudden transition, it may be that that's enough to cause failure. Our packaging will need to keep our internal relative humidity below this critical point, and we'll be talking how to figure that out in a minute. But this tells us One condition is a sharp transition, not associated directly with continuous functions, but discontinuous. By the way, to measure things like critical relative humidity, we what we do is we go ahead and make a slurry of a material and measure the relative humidity over the slurry. And that will give us a slurry, meaning having both water and solid present. So you have to have both present, and that will be the critical relative humidity. All right, the more general situation is the situation where we have continuous change. And this applies both for most chemical changes and most physical changes, although not all. So this will apply for things like chemical degradation, dissolution changes, amorphous crystallization. And this continuous change process is, is characterized by this equation, which is a modification of the Arrhenius equation. And there's a couple things that we've done to modify the Arrhenius equation. One, the Arrhenius equation normally describes natural log of a rate constant. But in this process, we've shown this ASAP process, we don't use a true rate constant because sometimes that's very difficult to know, especially for complex behavior. So what we do is we use a rate to the failure point. So this is a inverse of failure time, giving us a failure rate. We also have terms that are common in the Arrhenius, which is something called a collision frequency. So collision frequency is where we effectively have no barrier anymore. So in other words, the temperature goes to infinity. That's our collision frequency. We have an activation energy, which is common, a temperature in Kelvin, so absolute temperature. And then the other term that we've added, which is going to be very important for our packaging, is this B term, which is a humidity sensitivity factor. And this is multiplied by the equilibrium relative humidities. By equilibrium, we mean, again, not in packaged product, but letting it equilibrate. We'll look at that more in a minute. And this B term is very critical to understanding what the impact of packaging will be. So let's look a little more about this. First, to look at, for those who are more visual, so this is an equation way to look at this behavior. This is a visual way to look at that. And so what we have here is a plane, which is defined by this. So this axis here is really the classic Arrhenius equation where we're plotting ln k versus 1 over t. The intercept is ln a, and the slope is EA over R. This other axis, which is our humidity axis, this it's missing the symbol here. This should be humidity. Oh, here it is, relative humidity. This tilt in this direction is our B term. So we are going to, in accelerate conditions, work out here to predict behavior at ambient conditions down here. So it's always nice to look at some real products. So this is aspirin tablets. And what I've done is shown a set of data, taking just some of the data that we generated and looked at it in two different ways of looking at it. One way I've looked at it is by taking the classic 1 over t versus ln k, so the Arrhenius equation, at different temperatures, and I've done it at two different humidities. So at 20% humidity and 75% humidity. And if this equation is correct, that should give parallel lines. And indeed, we see basically parallel lines. Different humidities give different reactivity parallel to each other with temperature. Similarly, we could take the data and look at it in the other direction, where we've taken now the relative humidity versus the log of the rate and said, well, what happens at two different temperatures? So I just picked 50 and 70 degrees from this, and now you can see again parallel lines as expected. So this is the general behavior that we see, the behavior as a function of humidity, and this says that that's exponential, and the behavior with respect to temperature, which is exponential in 1 over the absolute temperature. So these activation energy and B terms are not something most of us maybe look at all the time. I suppose I look at it all the time, but let's look at what does it mean when you have these behaviors. So this is a set of data we took from the FreeThink database of many products. These are just drug products, not drug substance. And what I've done is just shown you there's quite a range here. The average product is right here. So what I've done is said, let's separate out the terms and say, how much impact does having a high or low or average B have? So if we had a low B would be around 0. And you see there are some products down in the 0, close to 0, even maybe a little bit of negative. And if you have 0B, that means humidity has no impact. So going from 60 to 65 to 75% humidity, a 3-year shelf life stays 3 years, as you would expect. The average product, an average B of around 0.04, would go from 3 years to 2.5 years, going from 60% to 65%, and drop down to 1.6 years, going to 75%. And then a high one, which still has a fair number of products, we would go from 3 years down to just 9.3 months if we went from 60 to 75% humidity. Now, one of the things that's kind of interesting here is the range 65 to 75 is a 10% relative humidity swing. And it's interesting because the ICH guidelines allow a plus or minus 5 or a 10% swing to be called the same humidity, as if that's not critical, when in fact, depending on the product, it could be very critical. Now, we're going to see, though, that it's not necessarily clear what you want. So what I usually say to people is, if you have a low B, close to 0, I say, congratulations, your product is going to be very robust, and you can choose whatever packaging you want, and the stability will be about the same. If you have a high B, I can also say, congratulations, we can make your stability very high by choosing the right packaging. So depends on how you look at it. Low B is not going to be very sensitive to packaging. High B will be very sensitive to packaging. Next, let's look at the same thing with activation energy. Now, I'm used to working in kilocalories per mole, but in many places, people are used to kilojoules per mole, so we can just convert them. So I put this average product is about about 29 kilocalories per mole. And the low and high, so if we look at that, the low, the high, are a distribution and account for the majority of products. The average activation, so the average product, a 3-year shelf life at 25 degrees would drop down to a 3-month shelf life at 40 degrees. So you notice that this is a much bigger impact than what's often considered by guidelines. So there's a lot of people who are used to an old rule of thumb that you double every 10 degrees. And that's approximately true at the very low end of activation energy. So a 9-month becomes 1.9 years, so just about double, going from 40 to 30 degrees for a very low activation energy. But the average product, in fact, it's much more than that. And you can see that we can have a product go from 40 degrees to 25 degrees, go from a 3-year shelf life down to 1 month shelf life with a 40 kilocalorie per mole activation energy. Just to kind of put things in perspective, if we had an average product, so exactly 29 kilocalories per mole and 0.04, of course, there's very few things that sit right at the average. In this case, none of the products sit right at the average. But if we say an average product, 6 months at 40.75 would be equivalent to 9.5 years at 25.60 in the absence of packaging. So it just shows you something we'll see later, that in many cases companies develop packaging based on 40.75 6-month decisions, and they're often over packaging the products and will pay higher prices for over packaging for many years to come. So how do we determine B? Well, that's part of what ASAP we do. We design our experiment, we get all the data, we plug it into our ASAP Prime program, the software, and we determine B, and then we can determine the degradation rate at any relative humidity. So that needs to do that, we're going to need to determine the relative humidity inside a package. Um, Normally, this is not a big deal if we're using a impermeable package because it'll just be whatever it started at. But let's look at what happens with a permeable package, because now the relative humidity inside a package will change with time. So how do we calculate the relative humidity inside a package? So just for examples, we can look at other examples too, but as examples, I've picked bottles and blister packages. And in the bottles and the blisters, the bottles could have a desiccant, the blisters can have different functions too, but water can get in, water can go out, and water can distribute. So here are the factors that are going to impact the relative humidity inside the package as a function of time. One is the moisture vapor transmission rate, which is a function of temperature. So this is something to keep in mind. A lot of people use MVTR data based on guidelines, but that's at a specific temperature that may not be the temperature we care about. In general, it is not. And it is very temperature dependent, so we have to know what that temperature dependence is. The relative humidity inside and the relative humidity outside are very important because the rate of moisture transfer is directly proportional to this difference. So a very high, or whatever the humidity is outside, as the inside starts to get close to that number, the rate of moisture transfer will go down. The next thing is that the materials that are inside the package, whatever they are, tablets, capsules, soft gels, anything, they absorb water, but their water absorption depends on relative humidity. And this is described by their sorption isotherms. So this will be a factor as well. How much material do we have there? Do we have a lot of material? That'll make a difference. And how much water does it come in with to begin with? So the initial water content is also going to be a critical parameter. And then if we do add desiccants, they have sorption properties, and that'll affect things. One of the things that people tend to think is important, we'll see over and over again, is that headspace is not important. Moisture, headspace volume and headspace moisture really play very, very little role. And we'll look at a couple examples of that in a second. So what is a moisture sorption isotherm? Just to look at a couple moisture sorption isotherms, I picked a couple examples. This is a classic generic crystalline API, but they don't vary much. Crystalline materials absorb very little water. That's because the waters that they do absorb are on the surface, so it's adsorption with a D. They absorb very little, and it's based on their surface area. So here at 50% relative humidity, this is absorbing, about 0.14, 1.13% water by weight. Very little water picked up. This doesn't count any waters of hydration, which don't really contribute to water activity. Here's a pretty common excipient, microcrystalline cellulose. Even though called microcrystalline, it's an amorphous material. And so here, in contrast, if we look at 50% relative humidity, we're absorbing 5.5% or so water. So this picks up a lot of water. And we're going to see that's going to make it so that excipients that absorb a lot of water are going to help us by keeping the relative humidity from going up as fast. So when water comes into a package, instead of it raising the water activity or relative humidity of the system, it doesn't do as much because the excipient can hold a lot of water and will buffer that change. And just as another example, here is a hard gelatin capsule, and at 50% relative humidity, it picks up almost 12% water. So we get quite a range here depending on the materials. Desiccants are things we can add to packaging that can absorb a lot of water. They depends on what kind. So there's two broad kinds that we use typically in pharmaceutical systems. One is silica gel, that's probably the most common, and the other is molecular sieves. So silica gel does not have a fixed capacity. So here's a curve for silica gel. And as you can see, as we go up in relative humidity, the amount of water we can absorb goes up as well. So at 50% relative humidity, this silica gel can hold about 25% water. Whereas if we're at 20% relative humidity, it's maybe 10% or 11%. In contrast, molecular sieves, which are also called zeolites, have little pores in them that are right size for water, and either water binds or it doesn't bind. So you get basically a flat curve, and the sorption stays flat. It does have a fixed capacity. So once it's filled, we end up basically um, uh, having no more capacity. So the result of that, here's an example where I have a tablets in a tablets in a bottle, add desiccant, and look at the relative humidity as a function of time in two different circumstances. So in the black line, I've got our silica gel. So what you see is the silica gel definitely is able to desiccate. I didn't show you without the desiccant, but without the desiccant, it's quite a bit higher here. But what you see is it gradually goes up. And if we pick the 2-year point, the relative humidity here is about 35% at 2 years. In contrast, if we look at the molecular sieves, they're significantly drier inside the bottle for the same 1 gram of desiccant. And for 1 year, we're definitely better. But by 2 years, when the capacity is exceeded, now the silica gel outdoes the molecular sieves. So it's important to understand this difference and use that in our calculations, which we do. And there are times where we do need molecular sieves, and there's times when silica gel, and there's even times where we would use a mixture of the two. So this is just part of what we're dealing with. Oh, I forgot to mention a little plug for some articles through here. This was just an article we published, and any of the articles that you have trouble getting, just go on to the FreeThink website. I think you can find all the articles or send us a note. But this was one that I think some people found interesting, which is a perfect barrier like foil does not perform as well as bottles with desiccant, because the desiccant can actually pull moisture out of the tablets and lead to greater stability. There's recently been advances in putting desiccants into blister packages. One of those examples is a desiccant embedded into a polymer, which is then heat stamped onto the lid stock for thermoform blisters. And that looks quite promising and works quite well. And again, another publication that we contributed to on how to do this calculations, but also the technology from, in this case, you can see the article here in Pharma Industry. You also could put a blister card in a pouch and put a desiccant in the pouch and perform that function. Now you'll have a separate stability once you open the pouch, but a lot of times that's acceptable. So before we get more into how we do some of these calculations, um, it's worth considering the question of how fast is water picked up by things. So, water comes into a package, a bottle or blister, let's say, and it's got to equilibrate into the tablets or capsules. And so, one question sometimes people wonder is, well, how fast does that occur? So we've been able to look at that in a number of systems, and I've just picked one example here of just a standard tablet. And what we're looking at is how fast is the moisture picked up, and that process is approximately first order. Now, there will be deviations in some cases, but in most cases, it can be approximated as first order. What that means for those who are not the math whiz people, that means that if you took the log of the relative humidity where you are minus the relative humidity of the final state, or in other words, if you start at one humidity and you take the difference with the humidity of where it's going to be, the equilibrium humidity, how long it takes, this log of delta versus time, you get a straight line. So basically, the moisture uptake rate can be described by a half-life. What that means, let's kind of look at this. If you're putting something at 80% humidity and it starts at 20%, so to go from 20 to 80, okay, well, we don't know how long it's going to take to get 20 to 80, but we know if it has a 69-minute half-life, to go from 20 to halfway between 20 and 80, so 20 to 60, so that would be to 50, would take 69 minutes for this tablet. And it would take another 69 minutes to go between 50 and halfway to 80, so whatever that is, 65. So each half point will take about the same amount of time. So typically, we could say that it'll take several half-lives to get close to equilibrium. So let's just get some orders of magnitude. For uncoated tablets, it's on the order of about an hour, the half-life. For powders, it's much faster. Film-coated tablets, it can slow this down to 2 to 4 hours. Capsules, 2 to 8 hours, depending on factors. Moisture barrier coats don't really make much difference. So all this basically says is, on the time scale of stability, which is usually measured in months or years, equilibration of dosage forms is essentially instantaneous. And so that allows us to do a lot of approximations. So how do we use ASAP to calculate packaging impact? We determine the product's sensitivity to relative humidity or temperature. We determine whether that's sudden or continuous, calculate or measure the moisture sorption, use the packaging or measure, and then set values. So what I'm going to do is let's try looking at a couple of examples of this. I'm going to shift to looking at an example here. So here's an example product that we have continuous behavior. This is not real data, so just bear with me. And what we see is the blue line is the mean predicted. Green and red are one standard deviation around that. But since most people like to use a 95% confidence for success, the green line is now the 95% confidence. So what that says here is, without packaging, we can have a 95% confidence that this product has a 1.3-year shelf life. Now, if we wanted a 3-year shelf life or 2-year shelf life, depending on our condition, what do we need to do? So if we put it at 2 years, our probability of passing without packaging is only 44%. So let's look at what happens with packaging here. This product, I've created a formulation which has drug and some excipients, has a moisture sorption behavior such that at 50% relative humidity, it will pick up 4% water. If we were at 25% relative humidity, 2.3. So we know how it holds water now. Now, right now, I don't have it in a package, so we're at 25 degrees, 60% humidity, so we're flat and it's at 60% humidity the whole time. Let's see what happens if we put it first in a bottle. So we have a lot of bottles, but the most common bottle that's used in pharmaceuticals is a HDPE bottle, and we're going to put a heat induction seal, the foil top on it. We can look at how much difference that makes, but just to kind of see what happens. Now, I've put 30 of these tablets in there, and let's put it in a 60 cc bottle and see what happens. Well, now it's pretty dramatic. We even can say with a 3-year, we have a 99.9% probability of passing. And the reason is if we started at a 35% relative humidity inside the package, in other words, the tablets at a water activity of 0.35, we are only at 44% after 2 years. Well, that's pretty good. What would happen if we removed the tablets and only had, let's say, 3 tablets instead of 30? Well, some people would say, oh, there's a head speed increase, but that's actually extremely minor, and doesn't impact. What happens is those tablets absorb a lot of water. So if we have fewer tablets, we're now going to be less stable, and now we only have a 22%. So the other thing you'll notice, by the way, is the humidity is going up with time, and the degradation rate then is going to accelerate as the humidity goes up. So this is one of the reasons that ASAP is more accurate than traditional stability, where you would take the 1-year time point and say propagate it linearly, which we know it's not linear behavior. So because we have the underlying math better, we're going to be more correct here. Let's look what happens with this one. If we go back to our 30 tablets and now see what happens if we decided we're going to bring this, well, I know there's a lot of people on from Brazil. So let's say we bring this to Brazil, which is a zone 4B country, and see what happens if we bring the product there. So if we go up in temperature, 2 things happen. The permeability of the package goes up, and the chemical stability is going to get worse. Now, if we bring from 60 to 3075, our probability of passing for 3 years dropped down to 1.4 years. Well, we talked about using a desiccant. Let's see what happens if we put a desiccant in this one. So let's put 1 gram of silica gel and see what happens. And indeed, that looks good, 99%. I wonder if a half a gram would be good enough. No, it doesn't give us our 95% probability. So we would need 1 gram in this case for that. But if we wanted maybe just a 2-year shelf life in Brazil, now a half a gram is more than enough. Maybe no desiccant is needed. No, we do need desiccant. We would just need a half a gram. Now, if we go back and now look at what would happen in a blister. So blisters have the property typically that the more expensive the blister, the more protective the blister is. But, so we often want to know what we need. Now, let's just look at what would happen if we select the blister needed in order to get a 4075 6-month shelf life. So first, we're okay in the bottle, but let's go to a blister and let's start out with a blister like this one. Well, this one is a low-grade Aclar, and you could see that it's just not going to pass at all, 0% of passing. What happens, though, if we went to 2560? Let's start with, let's say, go intermediate, 3065. Do we get 1 year shelf life? Let's see. So let's put this at 1 year. And the answer is easily pass 3065 intermediate for 1 year. And let's see what happens if we went 2560. And at 2560, we will get our 2-year shelf life, although we're not going to get a 3-year shelf life with this particular packaging. So the point is we could make the decision on packaging long term or even decide to put it up in parallel, not live with a more expensive package. So if we decided we needed to pass 6 months at 4075 because that's what we've always done, let's see what would need to be the level of protection needed to get that to pass. So let's go ahead and use, let's see if a 4 mil Aclar, yeah, 4 mil Aclar would pass, maybe a 3 mil Aclar would pass. Yes. But 2 mil Aclar would be right below our standards. So we see that we would end up packaging more than we would necessarily require if we went to that. All right, I'm going to go back to our slides. So I want to look at a couple other things. One of the things to look at is how does a bottle size matter? So in this case, I've got a 500 cc HDPE bottle with 30 capsules versus a 60 cc bottle with 30 capsules. So in this case, it's not the headspace, but the surface area, meaning the higher permeability, makes this less stable. But if we fill to 80% capacity, we see that we're going to be much more stable with the larger bottle. Larger bottle. So this is one of the factors. As you go to bigger bottles, you tend to get more stable if you keep the fill the same. So again, not headspace, but the fact that the surface to volume ratio is in our favor. Also, if we look at the headspace moisture, if we had 30 capsules in a 60 cc bottle and the capsule water activity was 0.35 or 35%, if the headspace was 30%, it will equilibrate to 0.350. If instead the headspace, the packaging room RH was 75%, that would only increase, the headspace would only increase once we close the bottle, the system to 35.2%. So headspace moisture is not a major contributor. We can also link the packaging decision to what we use for the initial water. So for example, in this case, I'm using cold form alu-alu foil. I can use a 4.7% water, and that's what I need. If I use 4.7 with an Aclar, I fail miserably, as you can see, for 3 years with the 4.7. But if I were willing to reduce this to 2.5%, I now have a very high stability. So it can be important to set the water specification linked to the packaging decision. And that's something we do quite a lot, which is what should the water content be at release, not what is it just because of what we used historically. All right, we're going to do briefly what happens with oxygen. Oxygen's complicated because it does impact drug product stability. First thing is oxygen is consumed by oxidation, and our drug degradation is sensitive to the oxygen level as well as relative humidity. And then our oxygen transmission is proportional to the oxygen level inside the package. So experimentally, we have to do a couple things. So the first part is to do the oxygen consumption. So first we're going to focus on oxygen consumption. We use saturated salts. They're degassed and then equilibrated to the oxygen level. We put in a jar, sealed jar, an oxygen dot that allows us to measure oxygen, and we put a fixed level of oxygen here. Then we minimize the volume with glass beads, at which we can then determine the volume afterwards by backfilling with water. These samples are placed in ovens, and the oxygen level is measured in the jar as a function of time. And from this, we have an equation. So this part looks very much like the equation we talked about already, the humidity sensitivity, temperature sensitivity. We've now added a C term, which is our oxygen sensitivity factor. And this factor is parameterized against 21% oxygen such that at 21% or in atmospheric, this term goes to 0. So we can do designed experiments. This is just an example where we have uh, LNK, so again, this ln1 over T iso um, of oxygen consumed. And from that, we get a slope, and that slope is our C term. Now, we do this at a range of temperatures and humidities. We're going to get the C, the B, LNA, and EA. So that's the oxygen consumption. We also have our oxygen sensitivity, and that's using the same equation, but now we're going to analyze oxygen degradation, and this will often give a different C term as well as EA, LNA, and B than the oxygen consumption. This, unlike the last case where we wanted to minimize the headspace because we wanted to have sensitivity to see the oxygen change, here we need a large headspace in order to prevent the oxygen concentration from changing during the course of experiments. So if we had about a 1% oxygen in here, we're going to need about a 1 liter oxygen source here, or headspace, to prevent the change from impacting the stability. Okay, so this makes oxygen calculations a little more complicated, but this is something we do quite a bit. Now we add that the packaging is permeable to oxygen in general. So as oxygen decreases inside a package, so we're consuming oxygen, the oxygen transmission rate will increase. So the oxygen consumption rate decreases based on the C term, and we're going to eventually reach a steady state oxygen concentration. So in order to do that, we also need to measure the oxygen transmission rate. And we do this on the real blisters or bottles, not on sheet data. And we do this where we put the bottle or blister or whatever the container is in one of these vials. We use our oxygen sensitive measurement, and we'll go ahead and measure the change of oxygen as a function of time, controlling the temperature. To do that, we'll use the Arrhenius fit because it is temperature dependent. So what are the implications? The allowable OTR, with and without desiccants, of course, depending on the sensitivity of the product to moisture. It'll also depend on the initial headspace oxygen, so that might be one of the critical parameters, and then whether we're using an oxygen absorber, what the capacity is. So just as an example of a calculation, here's a calculation. The orange curve is the degradation rate, and you can see for this particular case, it fails the specification right before 2 years. And here's the oxygen curve, and we can see that the oxygen goes down pretty quickly, but it doesn't go quite, it's not all the way to zero. It never will do that. And the rate is still high enough that we do not pass. That's with a permeability of 0.05 cc's of oxygen per day. If we bring the oxygen permeability down to 0.02, this gets much closer to zero. And now the rate of degradation goes down. We have the initial burst due to the headspace, and then we're okay. So this shows you kind of how we can model oxygen consumption, oxygen sensitivity, oxygen permeability as a function, of course, of initial conditions and then whether we have humidity and temperature sensitivity of the reaction as well. So in summary, moisture protection, there are 2 modes: moisture sensitivity, the abrupt and continuous. Both modes can be modeled or measured and then used in conjunction with modeling. The moisture sensitivity can be coupled with the calculated environment inside packaging based on moisture sorption and moisture transfer to select appropriate packaging for stability. Oxygen protection, we need to look at oxygen consumption, which varies with temperature, relative humidity, and oxygen level. The degradation rates, which will also depend on the same variables, but generally to a different extent. And the combination of oxygen consumption modeling, including the permeability, can combine with the oxygen sensitivity modeling to determine appropriate packaging for options for stability. And with that, I'll remind everybody as I end that I will answer some questions. We have a few minutes, and go ahead. You should have a place to enter questions. And I will say that any questions that don't get a chance to be read out, we will answer offline to you individually. So don't worry, any questions will get answered. And with that, I'll turn back over to Elisa as the moderator.
Okay, great. Thank you. So as I said, please enter your questions. I will take some of them here and we'll answer the rest of them offline. Okay, one question is, you show different packaging materials and their effects on the stability of products. And the question is, how accurate is this function? You know, how is simulated data correlated to real data? And in ASAP Prime, are these data based on literature or our own experimental data?
Okay, those were lots of questions.
That was.
So the first question was how accurate is, well, I want to check these several parts. There's different things that we can ask on how accurate they are. The moisture curve that we generate here is extremely accurate if the sorption isotherm is accurate and the MVTR is accurate. Now, the moisture sorption database we have was all data we generated, but you know, it tends to be quite accurate. I haven't seen deviations. The packaging data, well, these are based on real data that we generated, but if you choose a bottle size, it's parameterizing the bottle, and bottle sizes aren't exact anyway. Same with blisters. It's parameterized against set numbers. So we do have the ability to enter specific real measured values, and that'll make it more accurate. As far as is ASAP accurately predicting real-time data, the answer is in general, yes. There's lots and lots and lots of studies on that.
As a follow-up, has ASAP Prime been used to justify packaging changes in regulatory filings?
Yes, it depending on the country, ASAP Prime has been used successfully for post-approval packaging reductions without any other data provided other than the, so there's what companies have done is had ASAP and the long-term data for the commercial product, use that to validate the ASAP model, and then used ASAP to justify a packaging change, packaging reduction, and that was accepted at least by the FDA in the US.
Okay, great. What is the impact of heat induction sealing bottles on moisture permeability?
Well, let's go ahead and take this example and see. So typically, there's an implication. So if we go back here to a bottle, right now I've got heat induction seal. Let's see what happens to this product if instead of a heat induction seal, I just use a pressure sensitive foam. So we can see the humidity is going up faster. And in this particular product, it would say that we would not be acceptable at 3 years, or not acceptable to our 95% confidence. The 50% confidence we definitely still have. So it does make a difference. Some products more than others, but also we have to be careful with screw caps. The torque, if it's not optimum, can result in leakage, and then you can end up with much higher moisture transfer.
Okay, great. All right. Can we also consider in-use conditions? So how can ASAP be used to handle in-use stability?
Well, I think there is a paper we wrote on that, but I'll say that broadly, there's many different in-use scenarios, and those will each take a little bit of calculations and figuring it out. So one in-use situation is a powder that's constituted. So the liquid and the, by liquid, that's going to have two different studies. If it's a blister in a pouch, you open the pouch, now you have the blister behavior before and after the pouch. Another situation is, let's say, a bottle, opening the bottle. Now, the easiest calculation, and the vast majority of time for the bottle with a heat induction seal that's open, the vast majority of time, if you're using the tablets within, let's say, 30 days of opening the bottle or 60 days of opening the bottle, the easiest calculation is just assume the bottle cap is open, and that tends to be acceptable.
Great,
But
thank
if
you.
not, there are ways of calculating.
Great, thank you. So I think we've run out of time. So thank you, Ken, for a really informative webinar. As I said, we'll be responding to the rest of the questions that come in, and also the slide, the recording of the presentation will be available through our website, www.freethinktech.com.